Welcome to the video on vector math. This is just going to be a quick recap of vector math because we find in TP that we end up using vectors quite a bit. So this chapter is just to, reacquaint ourselves or make sure that we fully understand what's going on with vectors. So as you probably remember from school, a vector is a displacement value. It's a direction and a length. So it has two components. It definitely has kind of a length that's telling us how long or the amount of displacement that vector represents. And then of course there's also the direction itself, which is going to tell us an x direction, y direction, and z direction. And a vector is represented, it's easiest to see it in MaxScript first. We can simply create kind of an array here. This is actually a vector representation. So we're setting a variable. And this vector has three components. A has an x component of 40, a y component of 50, and a z component of 90. So that's just kind of the basics of how MaxScript takes a look at vectors. In TP, we're going to go ahead and add a TP here to our scene. And we'll create a dynamic set called Math. And we're going to create a series of subdynamic sets as we go here to kind of just look at the different aspects of vectors. So we're going to go ahead and start off with the absolute simplest form of representing a vector in TP, and that is to use a helper called point3. And a point3 value, of course, means that there's three components to that value. And each of those is going to represent a specific part. We've got the x portion of that vector, the y portion of that vector, and the z portion of that vector. And it's important to remember that we are talking about the world coordinate system in this case. So this vector is really going to start at 0 and point in a certain direction and a certain length based on these values here, the x, y, and z. So let's go ahead and just create a vector, and then we'll look at how we can actually visualize it out here in the scene. Let's create a vector that, say, has an x component of 60, a y component of 40, and a z component of 0. We'll just start in 2 dimensions for right now. So this, what we have out here in our scene, to this circle here, the radius of the circle is 100 units. So this vector then is probably going to be, if we go ahead and count this out, it's, the x component is going to be 10, 20, 30, 40, 50, 60, and then the y component is going to end up being 40 units up from there. So our vector is actually starts here at the origin and points up and ends up here. So as you can see, the vector, this is our x component of the vector, corresponds directly with this x value. And then of course the y component shown here being that. And if there were a z1, of course there would also be a z component. But currently there is not yet. So what we're going to go ahead and do is we're going to use a black box that we've created in one of the videos ahead of this called makeLine. And makeLine is a really great utility in TP just because it allows us to visualize lines in the viewport using particles. So let's go ahead and grab that black box. It's under the M3D helpers called makeLine. And actually we don't just want makeLine, what we want is makeLine direction. And we're going to have to do a little modification to this. Normally this makeLine direction black box, we've got a world raster which is going to define how finely the line is drawn. We also have a distance which just kind of comes with this black box by default, and we're going to have to get rid of that because part of this vector is obviously going to be describing that distance for us. So we can just go ahead and take this vector output of the point 3, connect it to that distance, and it will automatically calculate that distance of that vector. And then we can also go ahead and take that vector and feed it into the direction. And one of the reasons that we can feed that into the direction, and it's important to realize that a direction is different than an actual vector. This direction here, you see, gets fed and comes here into this unit vector expression. And a unit vector is what's called a normalized vector. And it takes whatever vector input we have, because as we mentioned, vectors can have, they can represent a very large amount of displacement. And what we're really interested in with direction is we just want to know the actual pure directional value of it. We don't want the actual length component, we just want to know the direction. So the way that's represented in TP is with a unit vector. So it's a normalized vector, and a normalized vector is what a direction is. So okay, so enough of that. Let's go ahead and let's just go ahead and duplicate this vector here, because we need a starting position with this black box. And we're going to go ahead and just rename this point 3 here. We'll call this origin, because we want that to be 0, 0, 0. Then we'll go ahead and zero out those values. Okay, let's go ahead and see if, okay, let's turn edit on the fly off so we get real-time updates. And you see we do not get a line so far. And the reason for that has to do with how this make line direction was built. It requires an on input. We're going to go ahead and disconnect that for that on requirement right now. And then what we'll see is that we get that being displayed. Let's go ahead and change that line color. Let's actually make it yellow for high visibility purposes. And then let's change the world raster. We'll drop that down so we can kind of increase how finely that line is drawn. And here what we see then, of course, is that we have a vector being shown where the x value, again, is pretty simply 60 units out this way, and the y component of 40 is just 40 units up. So this vector actually ends up exactly where we thought it was, thank goodness. So this is what a vector looks like in thinking particles. It has a direction component and a distance component. It can be expressed as 3 values. And so that's all pretty simple there. Let's go ahead and actually take a look then at, let's see. Oh yeah, what we want to do here is we want to actually go ahead and create some more black boxes that will show each of the components of the vector. And this is a pretty fun little exercise. Let's rename this point 3 here. Let's call this all caps vector, since it's our big important thing. And we'll put our world raster and origin way over here on the left, make a little more room. So this make line direction here, this is going to be our actual vector. So we'll just say actual vector. And what we can do is we want to actually show the x component, the y component, and the z component of this vector. So just so we can visualize it in space. And what we're going to do is we're just going to duplicate this make line direction. But we're also going to need some more particle groups, because we want to show those lines in different colors. So we're just going to grab a black box out of the M3D groups called colors. That brings in all these color groups here with their colors already set. And so what we'll do is for the x component, we're going to go ahead and draw that in red to conform to the max display color scheme. And then we'll have a y and a z also. And what we'll do for y, of course, is green, and for z, of course, blue. Okay, and so what we're going to do then is we're going to go ahead and we're going to show how this vector, what the x direction component is, what the y direction component, and the z direction component. And the way we're going to do this is, for one thing, we're going to go ahead and connect these world rasters to it. And what we need to know is that when we show these components, this direction value is not just going to be the vector. In fact, what we're going to be doing is we're going to be showing the specific x direction. And in this case, we're still dealing with the world orientation. So we can just create a simple helper here to represent the x direction. And this is how we would do that. We would put the x value at 1 and leave the y value at 0 and the z at 0. Okay, so this is the x direction. Oops, not that. We're going to have a y direction also. So the y direction is that way, and the z direction is straight up. So these are our direction components that are going to tell our black box how to, or which direction to draw the components in. So let's go ahead and take our y component. That's going to go in a direction. We'll pull the direction for x here, and this z direction there. Okay. And then again, we're going to need the starting position. Let's go ahead and set each of these also to the origin. And then finally, we get into the exciting part, which is the distance. So this distance, what we're going to do is we're just going to go ahead and take some of the outputs out of this vector and use the x value as the distance, and the y value for the y distance, and the z value for the z distance. And then we'll go ahead and scrub and update and see what we get here. We actually do get some blue particles for the z, although they are there is no height component just yet. Let's go ahead and add some z to this, and let's take a look. Actually, let's zoom in a little more. So here we are in 3D. Let's go ahead and start to raise our z component of our vector. And we can see now that we get these lines being drawn, this representing the x portion of the vector. And as we come out here, what we can see is that this x portion lines up and represents exactly how far to the right this vector goes, and the y line that we've got shows the amount of displacement in the y direction up to here. And of course we also have z, we also have z here, and z is showing us the amount of height associated with this vector. You can see that lines up directly across there. So this is basically using thinking particles to go ahead and create extra lines in the scene to visualize how these vectors are broken out into their x direction, y direction, and z direction. Okay, so this yellow line here is our vector, and these other colors are the components. Okay, so let's go ahead and we will leave this one alone for now. And then what we're going to do is we're going to take a look at vector addition and subtraction. And the way that we'll do this is we will simply take this vector dynamic set that we've got, and we'll just duplicate it. We'll disable the first one. We're going to rename this one. Actually, I'm sorry. What we're going to do is we're going to talk a little bit for a quick moment about normalized vectors. So we'll call this unit vector. Unit vector, actually, we don't need all these goodies. What we'll do is instead we're just going to go ahead and use a memory operator. And the memory operator will go ahead and store a vector. And we'll go ahead and add that to the inputs. And then what we'll do is we'll just go ahead and feed this vector into that vector unit. Actually, that's not a very good name for it. Let's go ahead and just take off that unit. And then what we'll do is we will show this parameter to debug. We'll come up here to the master dynamic, turn on debug mode, and we'll take a look and see at what value is coming into this memory node. Remember, this using memory is a great way to debug stuff like this. So the memory node's got an input called vector, and the value that's coming in is equal to 3 components. We get the x of 60, y 40, and z of 70 and change. So what we see is just that, a little bit of rounding there. But okay, and so what we want to understand is that there are 2 different types of vectors, at least. There's the regular vector we've looked at, where the vector can have a full, oops, you know, my drawing colors have gone away, sorry. Let's see if we can fix that. Okay, there we go. So as we were saying, we can have a vector that has a length greater than 1, you know, all the way out here to a length of 100, where this circle's at. But in our case, we want to take a look at unit vectors, or normalized vectors, as they're commonly called. And a normalized vector, as we've said before, is actually a vector that represents the direction component of this vector. So its length, the total length, is only going to be a value of 1. So the way that we get that in TP, we'll go ahead and just construct this from scratch. We've done it before. But we'll just take an expression, and it can't parse that expression right away because edit on the fly is turned off. So it's trying to evaluate it immediately, and now we gotta hunt for a window. But what we'll do is we'll go ahead and just set that expression to 1 right now, so it's valid. And then we're gonna go ahead and add an input for vector. We'll just call it vec. And we're gonna add a new output output called vector, and this will be called unit vector. So here we've got unit vector now, and the way that we're going to handle this is by using the expression unit and then in parentheses the vector, and this is going to return a normalized vector, so a vector having a length of only 1. And let's take a look at where we get this unit vector information. Okay, this information is found inside the Max help file under expression techniques, and here you will find a whole bunch of different kind of methods that can be used in the TP expression operator. So anytime you're dealing with a TP expression helper, this guy right here. Oops, still can't parse that, of course not. So whenever you're dealing with the expression operator, it's a handy idea to refer back to the Max script reference, or I'm sorry, the Max reference for expression techniques. And almost all of these parameters here are available in TP. There's a few of them that are not, such as these predefined variables like frame, normalized time, seconds, ticks. I believe those are still not supported in TP. All the rest of these you can do radian to degree conversions and back and forth, hyperbolic functions, just regular old sine, cosine, and one in particular that we're going to take a look at here in a minute is the acos function. And what else do we have? All these work. I believe that the noise function does not work, but for the most part all the rest of these do, the if, vif, etc. Okay, so this is how we would compose a unit vector, and so its length is just going to be 1. Let's go ahead and back, and actually we'll jump into this first vector rule that we had. And what we're going to do, we'll turn off the components that we were making, and we're going to go ahead then and just take our unit vector, or our unit expression, take this vector into here, and then what we'll do is when we feed this into distance now, of course what happens is that distance, let's clear our right to debug and let's go ahead and expose our distance value. Our distance is really, really small, and so we got to zoom way in here. The actual distance, and I don't know if it's going to show up, does not show up here in that part of the debugging. Okay, so here what we see is the unit vector output of this calculation is returning a vector now that is much, much smaller than the numbers that we see here. And the reason for that again is it's because it's taking away that overall length and just setting the length to 1 and returning what those components look like when the length is 1. So let's see if we can get our world raster any smaller down here. And I don't know if it's possible to zoom way in or not, but let's actually check our vector. Is that world raster getting pretty small? So I think it must just be that it's so small we can't really see it. Oh, there it is. We're zoomed in too much. So here is a length of 1. We'll go ahead and just double check that. The fast way, of course, that we'll measure things is just by creating a line with the keyboard shortcut. And then as we move the mouse out here, we notice down here in the status bar the distance it's telling us is, well, it looks like maybe my raster's off or something. There we go. So, some reason it's not exactly 1. Can't explain that. But you'll just have to trust Max there. The unit vector expression is going to return a vector of length 1, which is basically just a direction parameter. And we see that direction parameter in some different cases, such as memory has a direction input, so it'll actually take in just a specific direction value. And TP is smart enough, of course, that if we were to feed this full vector here, which is a much larger, longer vector than 1, if we feed that vector into the direction component, whether it's on memory or any other direction input, I think also you can find one on alignment has one too. So this direction data type when TP makes this connection and feeds this vector over to memory, it's automatically going to convert that vector into a normalized vector, into a unit vector. So it's kind of nice that it does that for us. Okay, so that is the unit vector. We're actually going to wipe that rule out. And let's go ahead and get into some vector addition and subtraction. Oops, nope, sorry, psych. What we want to do is we want to take a look at actually the inverse vector first. So inverse vector is basically the directionally opposite version of the vector. So basically it's going to point in the opposite direction that it's currently pointing in. Let's go ahead and get rid of our, we'll just disconnect that output there, clear our right to debug, take our vector here, and our raster is still pretty a little too low. We'll increase that. Let's turn off debug, get out of our line draw mode. And what we're looking at now is this is of course our regular vector here, and the inverse vector of this, let's actually go ahead and make it 2 dimensions for right now. We'll take out that z component. And so the inverse of this vector here, shown in yellow as it currently is we're going to need the inverse of that. It's just going to be pointing in the exact opposite direction. Looks like I can't draw straight, but that's okay. So the way that we're going to do that is, well, one way is we've already got a black box made. We've got a whole bunch of black boxes dealing with vectors. We've got a section of our website dedicated to explaining all these black boxes, because as you can see there are quite a few of them. So our vector, we want one called inverse vec, and inverse vec is just going to go ahead and it's going to take a vector input called v, and then it's going to, this is an expression helper again, where we break it down and we say take the x component, or the negative x component of v, the negative y component of v, and the negative z component of v, and return that as a new vector shown in brackets there. So the vector that's going to come out of here is going to be pointing in the exact opposite of each of those directions. So it's going to be the inverse. So we'll go ahead and connect this inverse vector now into the direction. And what we'll see is that this is going to be pointing directly opposite. So just like that. And then what we want to do is we want to go ahead and look at it in 3 dimensions, because 2 is fine, but we can't live in 2D all day in TP. So let's go ahead and as we increase the z component, you remember normally it was, normally that would make it higher, going up in z, but in our case we're dealing with the inverse vector, so it's pointing down. Then of course if we, let's go ahead and do this. This is one of the things we love about TP, is we're able to go, once we've built this whole dynamic set, just hold shift and drag it out, and we go ahead and take a whole nother one. Of course, we're going to have to make a few connections to set these back up. We'll go ahead and take these distances, and let's also go ahead and take this direction, and we'll feed it straight into the actual vector instead of the inverse vector. So now what we're going to get is we're going to get 1 for the, let's go ahead and rename this. This will be the inverse vector, and this other one, way down yonder, we'll go ahead and move that up. And this is going to be the actual vector. So now we're going to have 2 vectors being shown here, and let's differentiate them by, we'll make the inverse vector color different. Let's go ahead and change that. Oh, let's make it pink. And so now we get, it's kind of more of a little violet color, but whatever. So now we can see these 2 different vectors. We've got one that points in the pure direction specified by our vector, and then the other one is being created by this inverse vector. So it points in the exact opposite direction. And it also has the same length, the same distance component. Okay, so that is our inverse vector discussion. Inverse vector, just as an aside, comes in handy a lot when we need to, oh boy, certain situations you want to not only just look at which direction something is headed, but also look in the opposite direction. So opposite direction, very much an inverse vector kind of function. Okay, so let's get into vector addition and subtraction. Okay, for this, we're going to change this up a little bit. We're going to go ahead and duplicate that dynamic set, and we'll call this vector add subtract. And we'll disable this first dynamic set, so it turns off one whole set of those versions. It still has this current logic set up for this. So what we're going to do is we're going to flatten out this vector and just deal in 2 dimensions at the moment. We'll go ahead and we can get rid of that stuff. We don't need that. And we do not need the different components, so we'll remove all those pieces of logic. What we're going to do is we're actually going to be dealing with 2 vectors. We'll call it vec1, and we'll have vec2, of course. So vec2, we're going to go ahead, instead of being 60 units in x and 40 units in y, we're going to make it, how about negative 50 units in x and negative 20 units in y. So this vector is actually, when we represent it, we can actually easily just go ahead and see it here by reconnecting these. And now what we'll see is that it points and looks like this. So what we're going to do is we're going to show these 2 vectors. We'll call this vec1, and then we're going to go ahead and duplicate this whole setup. Let's get these set up correctly. World raster, direction goes here from vector 1. We need the distance from vector 2, the direction from vector 2, the world raster comes from here, the starting position up there. And then we'll go ahead and change, of course, the name of this dynamic set, but also change the color. So we're going to go ahead and let's make this vector draw in orange. Okay, so what we have is, let's go ahead and reduce this world raster a little bit. We've got our 2 vectors. We've got vector 1 in yellow. Looks like this, and then vector 2 looks like that. And so what we're going to do, let's get rid of that circle. What we're going to do is take a look at vector addition and then subtraction, just so we make sure we understand how that happens. And one of the big things to know ahead of time is that adding and subtracting vectors typically is done in world space. There will be cases where we want to actually use one of these vectors in its own coordinate system, and then add or subtract vectors based on that. That'll be, we'll either add a separate video or have a video on our website that talks about that. Okay, but right here we're going to go ahead and set up some math. We'll start from scratch. We'll build the expression operator, and of course we always get this error, can't parse expression, which is an empty expression. And the reason we always get that whenever we add the expression helper is because edit on the fly is turned off. So it's trying to update immediately. So it takes a look at this expression and says, oh, I don't know, I can't do anything with that. So the easiest way is we just usually punch in a 1 for there. And what we want to do is we build this expression is we want to indicate that there are going to be 2 vectors coming in. 2 vectors, vector 1 and vector 2. And then we're going to go ahead and do some math inside here, and then we're going to have a vector output. We'll call this vector result. Okay, so in our first case we're going to have vec1 plus vec2. We're going to see what happens during vector addition. So we're going to go ahead and we can take vector 1, add it here, take vector 2 from there, and then, let's go ahead and we'll just duplicate this make line again, and we'll call this vec result. And vec result, let's go ahead and make its display color, I don't know, how about red? So obviously some values are missing here. We need to get the starting position again, world raster, and then the only other 2 components we need are the direction, which we'll get from that vector result, and also the distance, which will come from that result. Okay, so this now we see it automatically updates, and this is the result of adding these 2 vectors together, or at least that's what it says it is. We're going to go ahead and double check our work here because, well, yeah, you know, that actually is correct. Because we have this orange vector, vector 2, is actually, it has some negative components. So when we add 60 to negative 50, what do we get? We get a value of 10, so it comes out there. And then of course 40 plus negative 20 is the same as 40 minus 20, so it only has a y component of 20. So this is correct. Go ahead and increase that raster a little bit here. But one of the perhaps easier ways to show this, instead of just showing the vectors like this, is we'll take this orange vector and we'll actually start it from the end point of the first vector. So what we'll do is we'll take our black box from make line direction, we'll take our starting point, starting position, and just connect it into the vector 1. So now you see that in fact we are getting, it starts with this first vector 1 in yellow, and then vector 2 comes here in orange. It looks like maybe the world raster is still too small, so yeah, there we go. So we end up seeing that we can have one vector here in yellow, the second vector in orange, and the result is actually just from 0 up to here. And it's important to remember that this starting position, of course, is determining how these lines are drawn. Right now, this vector result, the starting position, is coming from the origin, so that's why it starts there and points up there, which is the correct result in this world space. Okay, so that's vector addition. Let's go ahead and look at actually a fun experiment to do is to actually start changing the values of the vectors and then being able to see them update in real time, which is pretty handy in TP. So as we move these values, we can see these vector lines being redrawn, and we can see that as we change them around, we can see what the different results look like. So this is kind of a handy way to at least explore and see what the effect of changing certain values will do for us. For instance, let's go ahead and add a z component to one of our vectors, and let's switch this to the front view. So now we can actually see, this is our z indicator here going up. So the yellow vector has a z component, so it does point up in z, but this orange vector, vector 2, does not have any z value. So what happens as we add extra z value to it? Well, remember it's an addition, so it ends up creating the resulting vector with a higher z, whereas if we make that negative, then it decreases. So pretty straightforward. Vector math is fortunately pretty easy to understand, I think. Okay, so let's go ahead and switch this around. Let's go ahead and do a subtraction. And let's also change this out again. We're going to set these two vectors to have 0 z components to start with. Just makes it a little bit easier to conceptualize. Okay, and so what's happening here is actually correct. It kind of doesn't look like it, but we have to remember that what we're doing is we're taking this yellow vector and then we're subtracting this vector. And you have to remember that this orange vector, it has a negative 50 and a negative 20. So negative 50 in x, negative 20 in x. And so what happens is when we subtract that vector, all it really does is it ends up converting these negative values, because we're subtracting a negative. You remember from math class, that actually means adding them. And so we end up getting this, it draws first our vector 1 comes up here, and then vector 2, of course, is this. I don't have an orange color, but vector 2 being this, well, the negative version of this is going to make it draw a line up to this point here. So that's what vector subtraction ends up doing. Oops, keep switching over. Whenever there's a little problem with Camtasia, when you cancel out of that draw mode, it switches to some other screen. Alright, so that's subtraction. Let's go ahead and take a look, and we will start playing with these values a little bit more. Let's actually make this vector a positive vector, vector 2. If it has we can see the orange vector is vector 2. This is kind of what it looks like here. So this might be a little easier to understand since it has positive values. But it draws, when we subtract two vectors, it takes the first vector, vector 1, which is in yellow, and then it kind of adds negatively, which is what a subtraction is. So it subtracts vector 2. So it just takes this vector here and subtracts it from it. So it pulls it back here. It's basically kind of a negative vector would be the inverse vector. So when we subtract two vectors, we're taking the first vector and adding the inverse of the second vector. So this is how we end up with our new vector looking like this. It has most of the first vector, but it has a little bit of offset up to the side like this. Let's go ahead and explore with this. Oops, I added an extra key to my character into my function there. Let's go ahead and take a look at what happens when we start to add z components to it. Let's switch this one to the front view and we'll leave this in perspective. And let's take our vector 2 and so of course looking from the front view, actually let's not do quite so much there. Or actually let's do more. And we'll switch this to the top view. So what we've got with vector subtraction now with z components involved, we've got our first vector has some z component here, but our second vector has quite a bit more z to it. It's got a much higher z value, 61.5 versus roughly 30. So it's about double the z height. So what happens is when we subtract this orange vector, of course you can see that it's kind of creating a line down toward this point. So the resulting vector is as such. And then of course from the top view, our first vector, second vector, but when we subtract that x and y component, it comes back to here. Okay, kind of a long discussion on vectors, sorry. Just want to make sure that we get all the information out there and have a pretty thorough understanding. Because it can get a little hairy when we have a lot of vectors in TP, so you want to make sure that you can at least visualize and see what the vector is doing and understand vector addition, subtraction, etc. So there's a couple other functions with vectors that we want to take a look at, and that is the scalar product and the cross product. And we're actually going to look at the cross product first because it's kind of a fun one. So let's go ahead and check our notes. Okay, let's make a dynamic set for cross product. And cross product is going to be a little bit different. We're going to take most of the contents out of this dynamic set. We'll go ahead and copy those guys and paste them in here. And what we need to do is we're going to reorganize this rule a little bit, because when we deal with cross product, what I actually want to do is set up some user controls so we can actually move these around and watch the result happen in real time. So we're going to kind of rearrange what we've built here. We're not going to need these vectors. We will go ahead and keep this expression for vectors since we're going to modify that. But we don't need the make line direction anymore. And I suppose we'll keep this for now and just kind of see what happens. So let's go ahead and create some nodes so we can access these two nodes that we've got. First we'll pick node 1, point 1, which is out there, and then point 2, which is up there. So we've got our 2 points, and what we want to do is actually visualize those vectors. We've got a specific black box that will kind of handle that, and that is just make line. So make line, again, we've got a world raster value, we've got an origin, and we've got a target position that we're dealing with. So let's actually go in and check this make line. Let's make this draw in, say, red. So this will be our red vector, make line. Let's call that make line red, so we can easily understand in the viewport as we're working what it is we're dealing with. And we'll just go ahead and duplicate that, take the origin again, raster, and then finally the target position here is going to be going to this other node. This is point 2. Let's go ahead and call this green. And this red and green, it does not have anything to do with X or Y. These are just different colors for the vectors, of course. Let's increase that raster a little bit. We don't need it so fine. And so we've got those two being drawn. We've got this other make line direction vector. And so what we're going to do is we're going to take a look at what happens when, let's see, one moment. Okay, well, we're kind of missing some information here. These make line black boxes are calculating some things for us. And one of the things that they're calculating that we're going to need is we actually need a direction output out of here. Because we're taking a look at not only direction, but we'll actually output the direction, the distance, and the actual vector. So we need to go inside these make line black boxes, and we need to just pull out some information. We'll go ahead and pull out, let's see, which one do we want? This is iterating through all this, so we have to make sure that we only get the ones that we need. I believe it's definitely going to be that distance there, and that target position. This will be, oops, we pulled distance, not direction. Let's remove that. Let's take direction first, and then distance. And if we want to get our actual vector of that, we can go ahead and just take distance into this little svec calculation here and pull the vector from the direction. So what this is doing is we're just going to use this distance condition, which outputs both a distance and a direction, which are the two components of a vector. And we're going to just go ahead and multiply those again, s times v. So that's the distance times the direction. And this will kind of recreate that vector for us. So we'll go ahead and output that. And yeah, that's fine. And rather than reproducing that here, let's just go ahead and duplicate and reconnect. And then we'll go ahead and change this red. Whoops, change those to green again. Okay, so what we're going to do then is we're going to go ahead and take the vector 2, vector 1, and we're going to take a look at what happens in a cross product calculation. And a cross product calculation actually results in another vector. And the way that we represent this in math is it's our vector 1 x vector 2. Which is distinctly different than the multiplied sign, the asterisk. That results in a scalar product, but what we want right now is the cross product. So we're going to use the x, press enter to evaluate that expression. And let's go ahead and take a look at what we get. Let's go ahead and switch. Let's go to the top view, perspective. Okay, it has a rather large direction component. Curious about that. Let's see, are we in top view when we see these two? Let's actually pull this down. This is kind of the neat thing about being able to play with these in TP is that we can actually see these update as we shift them around. Of course, you can do this in any competent piece of software, but what is this guy's position? Let's set it x 100. It's got a little bit of a z value to it. And let's go ahead and change this vec result. We want to go ahead and draw this vec result in blue. Okay, so you can see that what happens is the vectors that are being calculated here, we've got this, I think this is our first vector here with point 0, this node. We'll go ahead and rename this point 1 and point 2. Get our mouse back in here. Okay, so from the origin to this point, this represents a vector. And then from the origin to point 2, that also represents a vector. Those vectors get calculated here inside makeline. And what we're going to see then is that the cross product of those two vectors results, oops, I've screwed that one up. Let's go ahead and get that back in there, vec1 x vec2. This results in a new vector which, as you can see, is pointing way up. I believe that must be a multiplication too. Normally we don't look at the cross product as the full vector output. Normally we just deal with cross product in terms of normalized vectors. So in order to do that, we'll actually not look at the full vector calculation coming out of this entire vector. We're just going to get the distance of that, so it's not so incredibly long. And the way that we'll do that then, of course, is we will just pull the direction values, which are normalized vectors, as you remember. So now when we go ahead and look at this, of course it's going to kind of totally disappear. It's going to be very small. We need to actually specify a separate float value for distance. So as we crank this up, this allows us to manually specify the length of this line, the length of this vector. But what's interesting here is that, and we're going to move this around in the XY plane. As we move this node, I want you to notice that that Z flips, the cross product flips that direction down when our second vector direction kind of crosses over the 180-degree line. So this is kind of an important thing to note, that kind of behavior. Okay, so this is a cross product, and we're going to take a look at this in our SC video, where we talk about proper reflection values. We use cross product quite a bit to help us generate either local coordinate systems when we have a single vector, or also when we deal with reflections off of collisions or intersect. Okay, so this is cross product. And finally, let's go ahead and we're going to take a look at scalar product, which is somewhat easier. Go ahead and again, we'll just duplicate that cross product, disable the first one, and rename this. We'll call it scalar product. And what we're going to do here is we have to modify this expression, because a scalar product, with instead of the x, we use the asterisk, the multiply sign. And what this does actually is it's going to return a scalar. So this vector result that we have here is not wanted. And something important we'll just add about expression helpers. If you have extra inputs that are not being used, or extra outputs, you have to watch out. Sometimes that can return a bad or incorrect result, or result in it not processing. So just remember, if you have extra values for expression helpers that you're not using, it's usually best to remove those, just because we've seen interference in the past where it doesn't calculate. So, but we're going to add an output, a scalar output. We're going to call this scalar product, and we're going to go ahead and remove our vector output. Okay, this vector line here is no longer needed, because what our scalar product returns is, of course, a scalar, and what that really represents is it's going to be a number, and we're going to turn on some debug so we can take a look at that. We're going to add a scalar value here. Depth of 0 is fine, we just need one of them. Make it an input, and we'll go ahead and pull that out of there. Okay, so what we want to look at, and we'll go ahead and turn on debug, we want to look at what does the scalar product really kind of represent. We're going to go ahead and move our point down here so that these vectors now are almost the same. And we're going to actually zoom way in and make them, let's pull this guy back up. I want this to be at 100 and 0. And point 2, we can go ahead and just make this as such. So you can see our scalar product result as it is calculating these two directions. Let's go ahead and swap this out. Let's actually just pull the full vector and see what we get. Of course, we get a much larger number there. This is not the number that we really want to be dealing with. When we deal with scalar product, again, we want to go ahead and deal with the just the normalized direction of the vector. So what we can tell is as this point comes closer to the other one, this value approaches 1, meaning what this tells us is these two vectors are almost the same. Whereas if we put them directly on each other, we do get a 1 result. So what this will do for us in TP is anytime we have two different vectors and we want to see how close or how similar they are, we can use the scalar product. Oops, and I always do that. We got to watch out whenever you have the expression operator highlighted and you start typing something. It's going to give you a bad result. So vec1 scalar product vec2. Okay, let's make sure we get out of that. And now what we want to do is go ahead and look at what happens when we get when this guy becomes 90 degrees. So with 90 degrees, what we get is a scalar product of 0. This tells us that these vectors are perpendicular to each other. So this is going to be one way that we can kind of detect vector similarity. And then as we go and this angle becomes greater than 90, what happens is we start to get into negative values, meaning at this point I am kind of headed in your same direction. It's very somewhat, 11.8% roughly the same. And then as we become negative, it tells us that this other vector is pointing away from or does not have any kind of the similar direction as the other. So then as we get all the way out here to directly opposite, you can see we're approaching -1. Let's see if we, yeah, I'm sure we could actually get that if we wanted to. And then of course as we come back around, we switch over, we turn positive again once we cross the 90-degree mark, and then we start coming closer to this other vector. Okay, so the scalar product is really about vector similarity, or direction similarity. Okay, and one of the interesting things that we want to go ahead and do with scalar product is we can actually calculate the angle between these two vectors by using a pretty simple little bit of math. With this expression, we're going to go ahead and duplicate it. We'll pull these two directions in, and then we'll actually add a new memory value called angle. Oops. And we'll go ahead and pull that into our input, and let's go ahead and connect this angle input here. And we're going to create a new function now in order to return the angle between two different vectors. So the mathematics for that's pretty simple. It's just the arc cos of vector 1 times vector 2, or the scalar product. The arc cos of the scalar product of two vectors. And so now what we'll see is, we've got to turn on debug. We can see that it's going to report our angle value now. And it's going to go ahead and tell us from this expression what is the angle between these two vectors. So we can see that the angle between them is very small, which also, we know from the scalar product that these are very similar vectors. And then we can see that as we cross over, we can see the full 90 value there. Actually, let's get that exact so we can go 0 in the x. So yeah, our scalar product being 0, our angle is 90. And then as we move further beyond 90, of course that angle will grow until we reach 180, and then it will kind of swing back around, and now it's becoming more similar so that it heads back towards 0. If you if you want to find out, and if you want to actually set up a system such that as this vector comes around here and when it crosses 180 it turns into a negative angle value, what you can do is you can actually calculate the cross product and detect which direction that cross product is pointing in order to kind of set up one of these sides, whether it's this side or this side, as your negative value. Okay, so this is what the scalar product will do for us. Again, just regular old scalar product will return either a value of 1 if they're exactly the same direction, or 0 if they're perpendicular to each other, or -1 if it's heading the opposite direction. And then of course, if the value is negative at all, then these two vectors are divergent. They're heading kind of away from each other. And then of course, also with the scalar product, we can take the arc cos of the scalar product of those two vectors, and that way will actually calculate the angle in between those two directions for us. Okay, well, I hope this hasn't been too boring. It's been almost an hour long. I think we've kind of covered vectors pretty well to set you up for working with TP, so let's go ahead and get into some more advanced stuff.